Accelerating deep learning by focusing on the biggest losers. So this is a paper that came out last year. Let's take a look at that. Accelerating deep learning by focusing on the biggest losers. Came out in October 2019. And the idea here is, instead of just traditionally training on everything, what instead we're going to do is, just look at the areas that we have the most amount of error, the most amount of problem, and just focus on that. And then if we do a batch of training on that, well, we're not going to have the error there anymore. Let's then focus on where we're going to have the next bit of error. And what they showed in this paper is that they were able to do the selective backprop and cut that down. What we're going to do is we're going to actually implement that. We're not going to redo all of their research. That's a little bit excessive, but we're going to look at two different ways of implementing that. So here is a Python notebook, and it is in Colab. Let's just take a look at that. This is a Colab notebook, and I was using Python 3 and a GPU. I'll put a link down below of where you can find this notebook. So I'm just going to go through the notebook quickly, show you the different areas I'm going to talk about, and then we're going to step right through all of the code and the data and see how that works and how you can implement this in just a few lines. Okay, so we're going to import MNIST. If you're not familiar with MNIST, it is a bunch of handwritten digits like this, 28 by 28 pixels. It's like the hello world of machine learning. We're going to define a model. That model is just a convolution neural network. Maybe in another video, I'll go into more detail about how convolution works. But for now, let's just leave it at that. That's how we're going to process the images. We're going to do regular training. And then there's this implementation I made that I call the worst training. And it just looks at the worst particular examples. And then we'll take a look at the biggest losers implementation, which is really similar to how the paper does it. We'll run some experiments with that, look at the accuracy, and then we'll go over some conclusions, some plots, and then I'll talk about how this affects unbalanced classes and my personal notes on this. Okay, let's get right into it. Let's go through all of the code. So we import the data. I already ran this ahead of time. It takes about an hour and a half to run it all. So I'm just walking through the code now. So we're importing matplotlib, numpy, some stats, and TensorFlow 2. This line here, if you're running TensorFlow locally and you already have the version, that's just a magic. You don't need to do that. This is just a magic thing for Colab. We're importing MNIST. We're just using the Keras default data set, and we see that there's 60,000 training examples, 10,000 test examples. We're just going to use that as is. That data is from 0 to 255 in all the pixels, so we're just going to divide that out so that it's from 0 to 1. A bit of normalization. Reshape it. This here changes it into being a one-hot encoding instead of just the numbers from 0 to 9. This is what we're training to predict, and then this is our output shapes. So this is our training set and our test set. Okay, it's just a plot function, and here's an example of plotting some of the digits. So you can see that, they're different shapes. The one isn't necessarily up and down, and there's just different penmanships, left-handed, right-handed, thick, thin. Here's some, this is just a pretty print for checking out what the neural net looks like. So in Python Keras, you can use this function called summary to give you some output, but I wanted to be able to display more of, what the dimensions of the network are. So here's the network itself. So this is basically 4 different max pools of convolution. I'll jump into each one of these in a little bit more detail, but at a high level, what we have is, we have our inputs, and then we have a first set of convolutions, and then we do a max pool, which reduces it from 28 down smaller, and then we do another couple convolutions, and then another max pool, which then makes it smaller, and so on. And then finally, we flatten that down, put that through a dense layer, do some dropout, and then our final output. Okay, let's get into it a little bit more. We're using this thing called Keras sequential model. Super easy for things that are just, one layer after another, nothing really fancy in between the layers, or different layers talking to different layers out of order. Sequential is the way to go. Super easy. The first thing we do is we say their input is 28 by 28 by 1. So there's these pictures of numbers don't have color. It's just black and white. And then we're going to batch normalize that. So, if we have a lot of black space, not a lot of white space on each of those pictures, that batch normalization will even that out. Or, if the corners are almost never used, then they get averaged out. And then we have two convolutions of a 5 by 5 window. So if the whole image is 28 by 28, then what this is doing is it's making 5 by 5 windows go across and then convert that image from one color in each pixel to 28 features in each pixel, using a 5 by 5 window to process all that up and turn that into 20 features. After we do that twice, so this second one is not using the pixels of the picture anymore, but the features from the previous layer. So it's doing a 5 by 5 window of the 20 features. So it's 5 times 5 times 25, different values, and it's doing that window and then converting that into 20 values in a new image. Then we do a max pool on that. So what that's doing is it's taking a 2 by 2 window going across the new image that we're making with all those features, and it's taking the maximum value in that 2 by 2 window for those 20 features, and then pushing that, making a new smaller image that's half the size. We do batch normalization on that. So we may have, definitely after we do this max pool, what we're going to have is we're going to have all high numbers effectively in the features in these filters. And the batch normalization is going to take all of those values, move everything to be an average of 0 and 1, 2, 3 standard deviations at 1, 2, and 3 value. We do that again, 5 by 5 window again, this time making more features. So the image is smaller. We're trying to concentrate more information in a smaller image. Do max pool again. So, what the max pool is doing conceptually is saying, first, what the features are doing conceptually is trying to, turn it from pixels into something more meaningful, like lines or circles or, a shade or something like that. And then max pool, what happens is, maybe one of the features is about lines this way. Is it noticing any lines this way? And some of the features are saying, yeah, I kind of see one. And then one of the features is saying, I really think that there is one here. Then the max pool will take that particular value. So after this happens, all of those filters will have fairly high values. What batch normalization does is it'll say, you were looking for lines like this all across the image and you found them everywhere with pretty high values. Well, I'm going to take the average of that put it to 0, and we're looking at standard deviations away from 0, away from the norm. So now that feature layer that was all about lines this way, it's going to be normalized. And so the values are all going to be, roughly between 0 and -1. That's the first standard deviation, centered at 0. And so you'll have different areas on the image that, we're pretty certain that there's lines this way, and then other areas where we're not too certain, or we're very certain that it's not that way. Even though we did this max pool, which is, just going to make all of our numbers high. So we do that again. And then finally, we have a very small image, but it's just got a ton of features. It's very thick, right? It's got a lot of colors or features or filters. We use all of those for the same thing. And then again, batch normalization, then flatten it. And so instead of it being, a square image with lots of filters, we stretch that out, and it's just a string of numbers. So that we can do this dense. So this is just another, your classic neural net. I've got one layer, and then I just make a fully connected other layer to it. So this one is 1,000 units. We do dropout, and then dense 10. I just made up this network. It works. I mean, it's not state of the art, but it does pretty well. And using that pretty print function, we can see this. So we can see what the name of that layer was and what the output shape of that layer is. So for these convolutions, we can see that the first one here, which said the convolution had to be over the valid area, it's going to be smaller than the input. Why is that? The input's 28 by 28. So this is our input. But our convolution is the square that goes by 5 by 5. And because we say that it's valid, we don't allow that square to go outside the image. Well, since the square is 5 by 5, we're going to lose effectively 4 pixels on each side, right? And so that makes it 24 by 24. But instead of one color, one feature or filter, we're now going to have 20. This next convolution, we say that we want the padding to be the same. We want the image to be the same number of X and Y pixels, height and width. And so we let that box, that filter, to go off the edges so that it's 24 by 24. And then you can see that this max pool, it divides it in half, right? We're taking windows of 2 by 2 and we're going across, and we're skipping by 2s also. Same thing here with all of these, all the way down here. And then this flatten, it takes this 2 by 2 by 80 image, right? So it's a 2 by 2 image with 80 colors or 80 filters or features. It's basically 80 units of information for each of those, for that 2 by 2 area. It's going to take all of that and flatten it. It makes 320. Well, that's 80 times 2 times 2. And then we do a dense layer, dropout. Dropout doesn't change the size. And then our output layer, which is our 10 different classes from 0 to 9. And our output layer is going to output a probability field because we said it needed to do softmax. Right? So it's going to do a soft maximum over that probability field. So if it thinks that there's a 70% chance that it's a 7, then in the 7 space, it'll be 0.7. And if it thinks that there's a 50% chance that it's 3, it'll be a 0.5 in the 3. But all of the probability has to add to 1. So in the example I just gave you, that's not possible. You can't have 70% of 7 and 50% of 3. But I think you get that. Okay. Then we just define here a test helper function. And what this test helper function is we can give it some training loss function, how many epochs or epochs, depending on what country you're from. We want to run this test for, what optimizer we're going to do, and with batch size. And then it runs the test, So it just compiles it, fits the training, compiles it again using, it doesn't matter what training loss that we specify during training. For evaluation, we're just going to use categorical cross entropy. And we're going to print out that information. Okay, let's take a look at what happens when we ran this. So this is just the regular training. We need a benchmark, right? We can't just make something new without measuring it against what we've already made. So here, we just use a regular training. We're just going to use, stochastic gradient descent, categorical cross entropy. We're going to run it 3 times and output the accuracy loss and elapsed time. So let's just remind ourselves what this accelerating deep learning by focusing on the biggest losers is supposed to really decrease this elapsed time and not really affect our accuracy or our loss. We're just supposed to make it faster, which is great. I mean, that's just, like unicorns and rainbows. Fabulous. Okay, so we ran this 3 times with just regular training, not focusing on the biggest losers. And we can see that we got to, the mid 98%. It's okay. So let's take a look at training on the worst only. So as I said before, I implemented this 2 different ways. There's the worst, well, I call it the worst, which is my take on it. And then I tried to implement it as close to the implementation as they had in the paper. And we're going to call that the biggest loser. Let's take a look at the worst first. So the paper describes choosing the worst from a training set, but we'll do it a little bit differently. Instead, we're going to choose the worst from the mini batch. So we're going to grab, for example, a batch of 100. We're just going to compute the loss of the worst 50 and train on that. And if we do it this way, it is so easy to do this in TensorFlow. So let's get into what this custom loss function is. The way we're going to do that is a custom loss function. For our loss function, we're just going to calculate only the worst. Let's take a look at that. So this is how you implement a loss function in TensorFlow Keras. There's this generator so that we can define any variables that we want. And then this is our loss function that we're going to return. And in TensorFlow Keras, a loss function has to have, it takes what the true value is and what the predicted value is. So we're going to use the already existing categorical cross entropy. This isn't anything new. The new thing that we're going to do is we're going to take that loss and we're going to use the TensorFlow top k function that's already built in to give us the top k of the particular error. And it just so happens that top k returns to you an ordered list that's ascending. So the first items are the lowest items. Great. So this top k is the lowest items of the error. And we're going to use just the k number of that. So in this, by default, it would use 25. And we'll return that. How is this even going to work? I mean, this is all we have to do in order to implement this paper. The majority of this paper, the concept of this paper, not the way that they say to implement it. We'll get into that in a second. But if you want to implement doing focusing on the biggest losers in a mini batch, this will work fine. What we're doing is we're throwing away all of that gradient information that is created in TensorFlow for anything other than this top k items. So in this case, if our batch size is 100 and we set k to 50, when we return the the first 50 losses after calculating the gradient descent, after calculating the back propagation and all of that, what we're doing is we're just destructively throwing away all of the rest of that gradient information. And then when we feed this into TensorFlow and we say learn from this, it will not learn all of that information, all of that other information. It will just learn this. And in addition to that, it doesn't do any of that other calculation either. And so it saves it about half of the calculation in the back propagation and in the update cycle. So here's a test for it. We're going to run exactly the same thing, except when we test our model, we're going to feed it the worst, this loss function, instead of just categorical cross entropy. And we're going to tell it to use the top 50 out of a batch size of 100. And we can see here that it got around 98% correct. And it only took, around 16 seconds as opposed to 24 seconds. Trained much faster and about the same accuracy. Actually, very close to the same accuracy. So that's taking the top 50 out of 100. Here's another experiment where we do 20% of the data by taking the top 50 out of 250. And we can see that we actually get, about the same accuracy, and we train in 10 seconds. Now, if we take this to the extreme and we have a huge batch size and we just focus on the top one, it actually breaks down, and there's a bit of a trade-off there. But training at 20% works fabulously and decreases training time significantly. Okay, let's take a look at how the paper tried to implement it, or close to the paper. There are some nuances to the paper that I'm not going to get into, so this is kind of a first blush at the paper. So the way the paper went about it, here it is. They talk about going through the whole training set, identifying the ones that it's having trouble with, creating a whole batch for that, and then training on that. And then they also, have this stale buffer where, they swap items into it and then reuse those instead of going through the whole thing in order to try to save more time. So there's specifics here that I didn't get into implementing, but the big point, the big focus of this implementation to get closer to that paper is let's go through the entire data set instead of in a mini batch way. Find all of the worst items in the whole training set and then retrain on that. So we need a new test function because the old test function won't work. We have this function that gets the worst. It masks out the worst items. So it goes through the whole training set, identifies which ones it's having trouble with, and creates a sub-training set with that. And we specify what fraction that we want. So we're going to try with 50% and 20%, just like we did with worst K. And then this test biggest loser model, this is very similar to the previous one, but focused. It had to make a little bit of a tweak in order for it to work with the biggest loser, with this type of get worst. So what we do instead is we just run the get worst to get our worst X and Y, and then we fit our model with that for one epoch, and then we go back and we continue that epoch again and again. So we can't specify the epochs here. Otherwise, it's the same. So similarly to the worst K, here the biggest loser is we're going to do 50% of the data, and our fraction is just 50%. So we can see that our accuracy is about the same again, 98%. And the elapsed time actually didn't shrink at all. There's optimizations that I might be able to make, but without getting too much into it, it's not straightforward to make those optimizations. At least what I could see. If you can see something after you go through this code, put it in the comments. I'd love to see that and take a look at how to do time optimization on that. And then you looking at 20%, where we're just doing 20% of the data each time we go around, our accuracy drops significantly. I'll get into some reasons why I think that is in the end, but 65% accuracy and still a large amount of time. So this didn't do particularly well. Let's take a look at what the graphs are. Here's just the calculating the data in order to make those graphs. And here's the percent errors for those different runs. So our regular accuracy, percent errors was pretty low. Worst 50 was was low. Worst, using worst K, 20% of the data was pretty low. 50% was pretty low, but 20% on the worst, on the biggest loser, was just horrible. So let's just ignore that and just zoom into these four. So we can see that the error increased slightly as we went from regular accuracy to worst 50, worst 20, and biggest loser 50. Not quite the same amount of accuracy, but mind you, the amount of time was way, way less. So here's the amount of time it took in order to do these different training scenarios. From 25 seconds down to just almost 10 seconds for that worst 20, which means that we could run that again. I did another experiment where I ran these, ran them all for a really long time, and they actually have very, very comparable long-term outcomes. The regular accuracy, worst K, and as long as you have a small fraction, biggest loser, they all come down for the same network. They'll all eventually get to the same accuracy. They're a little bit different. I'll get to that a little later, in how they get to that accuracy. But if you want to train up, it looks like this says if you want to train your neural net really fast, use a worst case. Use something like worst K. The biggest loser, as far as I could figure out how to implement it without doing too much optimization, it wasn't a whole lot faster. And certainly this one, which was faster, was so much worse with error. So that's our regular training, our worst only training, which was a super simple. It's really just this one line of code that changes it from doing this mini batch and training on the whole mini batch to just, the smaller error of that mini batch. And it really did amazing. The biggest loser algorithm, which is much closer to the paper, without me figuring out how to optimize the data flow, it didn't actually have any speed up. It was actually slower, and it performed generally worse. I think they put a lot of effort in the paper to figure out how to flow that data in a much more optimized way. So let's talk about unbalanced classes for a second, because These, using the regular or the worst K or the biggest losers algorithm, have a very different way that they handle unbalanced data. I'm just going to read this out. So both per batch and per epoch methods of focusing on the hardest problems totally changes your probabilities. So let's imagine that our training set really doesn't have very many threes or left-handed digits or some other unbalanced data. This training set, this MNIST training set, is super balanced. It's got 6,000 training examples of each. It's got 6,000 ones, 6,000 twos. It is super balanced. What we're going to do is we're going to imagine that instead of 6,000 of each, it only has 600 threes. If that's the case, then the algorithm could get 99% correct, 99% accuracy, if it got everything wrong other than threes. It just had a blind spot for threes. It just ignored threes completely. Let's say it just categorized them all as eights or nines or just random. It could get 99% because 3 is a small class. It's an unbalanced class. And that wouldn't be good because, well, we're not talking about threes really in a real situation, right? We're talking about a subclass, left-handed people, for example, or people who have a particular accent that live in a region. They're all a smaller demographic. And we want our neural net, we want our machine learning to do well with that smaller sample, just as well as it does with the larger sample. Now, if we use per batch or per epoch focus on that worst group, then suddenly the threes can't be ignored. I'll show you why. So let's say we're doing a per batch, worst K. If we focused on the worst 5%, right? So if we take a batch of 250 digits and we only look at the worst 50 of those 250, we take 1,000 digits and we only take a look at the worst 50. The threes will make up 1% of that, right? Because they are 600 out of 60,000. They'll make up 1% of all the digits. But out of that 1,000, remember they make up 1%, there'll be about 10 threes in there. But we take the worst 50, so there'll be 10 out of 50. So there'll be 1/5 of the training. And suddenly of that training batch, so that boosts their relative representation of 1 all the way up to 20%. So the gradient descent, the learning batch, can't ignore them anymore. It will not get lost. The system can't just say, well, the threes are really weird. I don't know. I don't see a whole lot of them. Forget it. I'm just going to focus on all the rest. By focusing on the hardest in a mini batch or in the whole per epoch, what you end up doing is you end up spending a lot more time focusing on these smaller groups. And that's really great. That isn't a complete fix for an unbalanced data set, but it certainly helps out a heck of a lot. So my personal take on this is I really like worst case. It was super easy to implement. It performs well. So I'm going to read this. This loss function will probably not work well with networks that try to do something Bayesian, like variational autoencoders, as it messes up the sample set probability distribution. Yeah, that's just a note of warning. I really like this worst K loss function. I've been using it quite a bit since I read this paper and implemented it, and it serves me really well. And it works up to, like just 5% or 1% worst case. All right, that's it. I hope you enjoyed this video, and I hope to see you in the next one. Have a good one.